Okay, so if we take this equation, which is just like the one we did before, except it's not homogeneous anymore, we get what we call a characteristic solution. Y equals a e to the negative 3t plus bt e to the negative 3t, which is the solution we got before. We know that solves the equation if this is 0. In other words, that this solution plugged into the left-hand side is going to give us 0. Okay? It's not going to give us e to the t, so we're going to have to add something to it in order to get e to the t out of this mess. It's fairly easy to figure out what. You see that? You've already seen it, but just summarizing. But whatever we add to this, this doesn't influence whether it gives us the e to the t or not, because this is always going to give us 0, right? So we just add something to this, and we're going to call that a particular solution. A solution, any solution that solves this equation will do it, okay? Well, in that case, how do we get the general solution? Well, okay, we get the general solution to the non-homogeneous equation, again, finding any solution to the non-homogeneous equation, any solution at all, any particular solution.
Are there more than one?
We'll get to that. If there is, it's the same as the other one.
Okay.
That's how you basically prove it. Okay, you find any solution to the non-homogeneous equation, you add that to the general solution to the homogeneous equation, and you've got your general solution to the non-homogeneous equation. It's real easy to find a solution here. As we said, if y is a polynomial, then it's not going to give you e to the t. Okay, it's going to give you something else. It isn't e to the t, okay? So, and you can prove that very easily. Any power function, any polynomial function. At the best, well, it can't possibly give you 0, and it can't possibly give you e to the t. A sine or a cosine, well, all the derivatives of sines and cosines are sines and cosines. Can't possibly give you e to the t. Okay? You know, there are other things you could try, but the obvious thing to try is an exponential function. And as we said, if you have e to the 5t, okay? I said e to the 7t before, but that sounded so much like 70, everybody got confused. Okay, no, nobody got confused. But if it's e to the 5t, then all these derivatives are going to be multiples of e to the 5t. You're not going to get an e to the t by plugging any multiple of e to the 5t into this thing, okay? And you could try t e to the 5t, but that's going to give you things that got t's in front of them, okay? At least this term will have a t in front of it, right? And so will these. So we're kind of stuck saying, well, looks like y is just going to have to be multiple of e to the t. So we try it. Let y equal some arbitrary multiple of e to the t. Plug that into the equation and solve for c, and we get c equals 1/17. And the details are so trivial that you all did it as soon as I asked you to. Not that you couldn't do non-trivial things, okay? Just plug this in, solve for c. All the e to the t's go away, you get a 1, a 6, and a 9, you get 17 e to the t. C e to the t has to equal e to the t, so c has to be 1/17. Okay, we add that, and we get our general solution. Okay, now I haven't proven that there's no other solution, but it just goes by basic. If there's another one, it's the same. Okay? We'll deal with that next time. Let's get the method going. Okay? Because I'm giving you several methods all at one time here. Okay, so let's take this equation. Now what are we going to try? Here we try to see e to the t for our particular solution, right? Well, no, any multiple of a real exponential, at least, is not going to give you this, right? Okay? You could try a multiple of a complex exponential, but not necessary, okay? How are you going to get a cosine of 2t out of sums of derivatives and higher derivatives of your function. What function would you take second derivative of, add some multiple of the first derivative, some multiple of the function itself to get a cosine of 2t?
Has to be some trigonometric function with 2t as its
Okay.
argument.
Going to use any tangents? Cosecants?
Maybe.
Turns out you don't need to. All you need is sines and cosines. Okay? Derivative of a tangent is a secant. So if you try a tangent here, you get a secant here and then a derivative of a secant here, you'd have denominators that aren't going to match cosine of 2t. Okay?
Okay.
That's a derivative of tangent's a secant, it's secant squared. You understand? Did I say squared
I think so.
before? Okay. See, I can't remember what I said. Okay. Anyhow, you get the idea. So the simplest thing you can try is sums of sine and cosine. And it's got to be sine of 2t and cosine of 2t, because if you got any other argument, you're not going to get anything with a 2t in the argument, and you got to have that. Okay? So,
It wasn't a mutation, it was a deletion. Mutation means the DNA got out of order, he had a strand of DNA that was just gone. That missing strand of DNA was code that said it was bonding on the middle of that artery.
some multiple cosine of 2t plus some multiple of sine of 2t. See what you get. So you can solve for C and D.